Newton's third law is probably one of the most commonly known statements that there is in normal everyday life, common ordinary statements of a physical law. And if I start it out, I bet you can probably finish it. Newton's third law is sometimes stated like this: for every action, can you finish it? There is an equal and opposite reaction. That's right. So Newton's third law is sometimes called the action-reaction law. But what does that mean? Now, although it is one of the most commonly known law statements that there is, it's also very, very commonly misunderstood. So let's write it down and then let's take a look at it very, very carefully. Newton's third law, the action-reaction law, states, whenever one body exerts a force on a second body, the second body exerts an oppositely directed force of equal magnitude on the first body. Now, to begin with, body in physics just means an object, a thing, some object. So some physical object exerts a force on another object. So very qualitatively, we've got one object, call this object 1, and it is applying a force on object 2. Now, these do not need to be in contact. These forces could be field forces, they could be contact forces, it doesn't matter. However these forces are being exerted. Let's imagine that object 1 exerts a force on object 2. So I'm going to draw in that force. Let's assume that it's a pushing force. I'll call this F2. That's the force on object 2. But I want to emphasize that this particular force on object 2 is being caused by object 1. So I'm going to call this F21. That's the force on object 2 due to or from object 1. So F21. It is a vector, so I'm going to write it as a vector. Now, if object 1 exerts a force on object 2, then, according to Newton's third law, the second body exerts an oppositely directed force of equal magnitude on the first body. So that tells us that object 2 must exert a force on object 1. Let's draw that in. We'll call that F1 because that is the force on object 1. But again, I want to emphasize that this is the force on object 1 from object 2. So I'm going to call this F12. Likewise, this is a vector, so I'll call this a vector, F12. What we know is that these two have to have an equal magnitude. In other words, the magnitude F12 must equal the magnitude F21. But they are in opposite directions. Well, how do we say that two vectors are in opposite directions? We just put in a negative sign. So this is telling us that F12 vector must equal negative F21 vector. So when one object exerts a force on another object, the second object must exert an equal but opposite force on the first object. Action, reaction, or action, reaction. Doesn't really matter. Usually I like to have a couple people come up or one person come up with me to demonstrate this, but what I'm going to do is I'm going to ask a couple people, could you two in the back? Yes, you two. Could you both start pushing on each other? Just put your hands up and push on each other. Okay, excellent, thank you. Now, let me ask, who is pushing harder? Is the person on the left pushing harder on the person on the right, or is the person on the right pushing harder on the person on the left? Well, according to Newton's third law, we know that the forces have to be the same. They have to be exactly the same in magnitude, but opposite in direction. So while one is pushing to the left, the other is pushing to the right. Excellent. Now, could you start moving in one direction? Both of you moving together. Keep pushing, but move in one direction. Great. Now, let me ask you, who is pushing harder? Is the person on the right pushing harder, or is the person on the left pushing harder? Which one? Well, it doesn't matter whether they're moving or not. They still have to apply the same force on each other, but in opposite directions. The same magnitude of the force, but in opposite directions. Thank you very much. Let's take a look at another situation. This is one that is typically a little more confusing for people. Let's imagine that we have a situation that looks like this. We've got a great big truck that is moving to the right, and a little tiny car that is moving to the left. And they're going to collide with each other. Now, don't worry, no one is injured in this demonstration. First of all, they're only stick figures. Let's imagine they collide. What happens? So the truck and the car collide, and what happens? They end up moving, say, off both together to the right. So the car is coming in, the truck is coming in, they collide, and then they move off together to the right. So what do we think? Well, we think, oh, obviously the truck must have pushed on the car more than the car pushed on the truck. That's what we might think, but that is not correct. The reason that we think that is because of the motion that we see. The car, which is coming in this way, is pushed backwards. It's completely turned around and made to go the other way. While the truck coming in is only just slowed down a little bit when it collides with the car. So there is a much larger change in the motion for the car than the change in the motion for the truck. The truck has a much smaller change in its motion. And we think of that then as showing how the forces must be different. The force that the truck exerts must be larger than the force the car exerts. But that is not correct. The forces are the same. The force that the truck exerts on the car is equal but opposite to the force that the car exerts on the truck. The car pushes on the truck this way. The truck pushes on the car this way. The forces are equal and opposite. So F truck car is the negative of F car truck. Why do we see something so differently happening to both? The car being turned around and forced the other way, and the truck just kind of barreling through. That's because the masses are different. If we know the forces are the same, then if FTC, the force on the truck, that must be the mass of the truck times the acceleration of the truck, while FCT, the force on the car from the truck, that must be equal to the mass of the car times the acceleration of the car. If these are equal but opposite, then we know the mass of the truck must be equal times the acceleration of the truck must be the negative of the mass of the car times the acceleration of the car. Let's divide by negative mc. What do we have? AC is equal to negative mt over mc times a truck. Well, what does this tell us? First of all, it tells us the acceleration of the car is going to be the negative of the acceleration of the truck. So the car, while it's going this way and ends up turning around going back that way, the truck is end up just going to be slowing down a little bit. So the acceleration of the car is in the opposite direction. But notice this, mt over mc, if the truck has a much larger mass than the car, the acceleration of the car is going to be much larger than the acceleration of the truck. The motion of the car is affected to a much larger degree than the motion of the truck. We see that and we think, oh, that must mean if you were to see a collision, you would think, oh, the forces must be very, very different. But no, the forces actually are exactly equal but opposite. it's the accelerations that are so different if the masses are different. Very, very good. Let's take a look at one more example. Oh, let me just mention that if you're in my class, there is a homework assignment that actually works through this and sticks some numbers in there, and we'll see that actually the forces do turn out to be exactly the same. Great, let's take a look at one more example. Here we have a very beautiful drawing of a horse pulling a cart. Now, whenever I draw this for my students, I get all sorts of comments. This is not a dinosaur. It's not, I don't know what else anybody ever thinks it is. It is obviously a horse. This horse is pulling this cart. Now, let's think about the forces involved. First of all, let's imagine the horse is trying to pull the cart forward. So, the horse is exerting a force on the cart. The horse is pulling the cart forward. So, we have a force like this. We'll call that the force on the cart due to the horse. Well, if the horse is exerting a force on the cart, we know the cart must be exerting a force on the horse, and we know that that force must be in the opposite direction with the same magnitude. So we've got a force on the horse from the cart. These forces are equal and opposite. Now, and forces always exist in pairs, like this. Anytime one object exerts a force on another object, the second object exerts an equal but opposite force, so forces are always in pairs, like this. Now my question is, how is it possible for the horse to pull the cart forward? If these two forces are exactly the same, equal but opposite, how is it possible for the horse to pull the cart forward? Because these are exactly in equal but opposite. Just think about that for a second. Well, it's a bit of a trick question. Remember when we started talking about the motion of an object. If we want to talk about the motion of the horse, we must consider only the forces acting on the horse. We're not worried about any forces that the horse exerts on something else. If we want to talk about the motion of the horse, we must only consider the forces on the horse forces. This force is a force on the cart. This is a force from the horse. We're not worried about that. If we want to talk about the motion of one of these objects, like the motion of the horse, we're going to look at only the forces on the horse. So, for the moment, let's ignore this force. So we've got a force on the horse in the backward direction. Now, how is it possible for the horse to move forward if we have a force acting on the horse in the backward direction? Well, because that's not the only force acting on the horse. Remember, to determine the motion of an object, we have to look at the net force, which means the total force acting on the object. Well, are there any other any other forces acting on the horse? Well, yes, there are actually. There are several of them. First of all, we know, now we haven't talked about this yet, but I think you can imagine, and we'll talk about it much more next time. Gravity is pulling down on the horse. So gravity pulls on anything downward. So there is a force pulling the horse down, and then the ground pushing the horse back up. We call this the normal force, and we'll talk more about that next time. But just for the moment, the normal force pushing from the ground back up balances the force of gravity pulling it back down. So these two will balance each other out. But then what else? There is a force from the ground pushing the horse sideways, forward. When you or anybody or the horse tries to walk forward, how do you walk forward? You walk forward by pushing off backward from the ground. You push your feet backward, and then that pushes you forward. So the horse pushing with its legs on the ground backward means the ground pushes the horse forward. So we have another force in the forward direction acting on the horse from the ground. If this force were less than this force, the horse would not be able to move. But if the horse can push on the ground harder than the force that the cart is pulling back on the horse, then the horse will be able to move forward and pull the cart forward. So, the bottom line is the horse needs to push on the ground with a force greater than the force the cart is pulling on the horse, and at which point the horse will be able to accelerate forward. Very, very good. Excellent. Now, next time we will take a look at some more examples of forces and how that affects their motion, and we'll actually do that for another lecture after that one too. Great. Well, I hope that was interesting. I will see you next time.